All right, so 56 and 10. And neither of those are prime either, right? So let's go with this 56. What can go into 56? Okay, 8 and 7. What goes into 8?
4 and 2.
And what goes into 4?
2 and 2.
Okay, so now what about this 10? All right, so we go through and we look at all of these terminating branches of our factor tree, and those become our factors. So what this says is that 560, number 560, is equivalent to, we got 1, 2, 3, 4 2s. And then, what, a 5 and a 7? So if we multiply all those out, we should get 560. Is it okay with everybody? All right, so the explanation that we went through yesterday, the day before, said, if I want to simplify radical 560, I'm going to look for groups of numbers. We're looking for pairs, which means we look for 2, right? 2 things. And a lot of times we're going to get 2 2s, okay? Because one of the main factors of a lot of these numbers, especially if it's even, is going to be 2, okay? So we're looking for groups of 2 objects, and those objects have to be the same. So in this case, a group of 2s. And then here's another group of 2s, okay? So when there is a group or a pair of a particular object, that object comes out in front, okay? So from that group right there, we got 1, 2 that came out. From this group right here, we get another 2 that can come out in front. And we're going to multiply everything that's out in front. If there's multiples, they all get multiplied together. And the things that are on the inside are the factors up here that did not have a like pairing. So 5 didn't have another 5 to pair up with, and 7 didn't have another 7. So what actually happens is that they themselves become a group. Okay? So 5 times 7 is what stays underneath. So what does this out front give you? 4. And what does 5 times 7 give you? 35. Okay? So that is the fail-safe way of coming up with a simplified radical. Now, that's not the only way, okay, but that will always work. So what I want to do right now is kind of talk about other alternatives for doing this, okay? At this juncture, we took 560 and we broke that down to 56 and 10, so I'll keep doing that. 10 went to 2 and 5, so we'll leave it that way. But 56 went down to 7 and 8, right? And then 8 went down to 4 and 2. We could actually stop there if we wanted to, okay? We wouldn't necessarily need to break the 4 down, and this is the reason, okay? That's 7, right? That's prime. 2 is prime, 5 is prime, 2 is prime. What kind of number is 4? It's not prime, but it's a perfect square. So what we're trying to really do here, remember the overall goal is to figure out what is the largest perfect square that divides into 560. 4 is not that number. 4 is not the biggest perfect square that divides, but it is a perfect square. The thing I want to kind of get you guys to visualize here is that what we're doing here is when we do our factor tree, we can actually stop when we recognize prime numbers or perfect squares. Because really what radical 560 means, if we go through and look at this factor tree, I'm going to just type it in to Desmos here so you can see the comparisons here. So if I type in square root of 560, Okay, so we see the exact value, or no, I guess not the exact value, the rounded value for that. If I type in the square root of, now I'm going to type this product in right here. So 2 times 2 times 2 times 2 times 5 times 7. Does that still give me the same decimal here? So does that prove to you that that is the same thing as that? Okay. So could I do this? Let's think about this. Let's go square root of 2 times square root of 2. So now I'm just taking each one of those factors and putting it in its own square root. Does that still give me the same result? Yeah. Okay. So what we see here is that the square root of a product, okay, that's what we've got right there. 2 times 2 times 2 times 2 times 5 times 7, that's a product. The square root of a product is equivalent to the product of square roots. Does that make sense to everybody? The square root of a product is the same as the product of the square roots. So we can do this. Now, let's make things a little bit simpler. So, and then this route here, I didn't reduce that 4. Okay, that root 4 would have reduced to 2 of these 2. So let's say that's that set of 2's we left as a 4. Does that kind of make sense? Is that product, square root of that product, still the same thing as radical 560? Okay, so down here, instead of those, it would have been that. Does that make sense? Okay, but what is the square root of 4? 2. So I could have it written this way. Does that kind of make sense? Okay, but look at this right here. Isn't that another 4? So if I put those in, is that still give me the 23.66 number? So down here, when I do it this way, this would be a 4. And that one is gone now. Still get that, right? But what's the square root of this 4? Still 2. So with that same number, right? Okay, so then I could take that 2 times 2 then outside and make that a 4, and it's still the same 23.66. Okay, and we could change so this 5 and this 7, those turn into that radical 35. But here's my next question. Go back up to this. What is that product? What's 4 times 4? 16. Is 16 a perfect square? So could I change so that 4 times 4 would turn into that outside the radical? Is that still 23? So what I'm trying to demonstrate there is that this 560, the largest perfect square that will divide it is 16. If I take 560 divided by 16, it gives me 35. Does that make sense, everybody? 35 ends up being that number that stays underneath the radical in this case. Okay, so this whole process, what we're doing, okay, this is we call this an algorithm, the way we're doing this, okay? But this algorithm will always identify for you the largest perfect square that divides the radicand, okay? If you do it this way, and I ever ask you, well, what is that largest perfect square? It is always the square of that number right there. Okay, so that number that came out was 4. If I square that, I get 16. That means 16 is the largest perfect square that will divide 560. Okay? So that logic, that understanding, hopefully, gets us to realize that when we are doing our factor tree, if, just to make it a little bit simpler, a little bit easier to work with, if you ever come across a prime number, obviously we've been instructed to stop it, okay? And the reason we stop at a prime number is because, let's say I get down to, we did 10 goes down to 2 and 5. Well, then that 2, if I didn't stop at prime numbers, would go to 2 and 1, right? And then that 2 would go to 2 and 1. And this 1 would go to 1 and 1. And I would never stop. Does that make sense? Okay, so you stop at prime numbers. But now, based off of this discussion we just had, we can also stop at square roots. Or not square, perfect squares. Because of how square roots and perfect squares work with one another. Okay, so let's do another one. Let's go 2 times 6 times. So the square root of 3240. 3,240. What number do you automatically know will divide that? You know 2 will, right? It ends in an even number. Now, you can do that, and that's fine. Nothing wrong with it. But if it ends in a 0, what is a better number, I think? Might clean things up a little bit. 10 would be better, right? Especially the bigger this number is, okay? At least just to make your factor tree a little bit maybe more condensed or cleaner looking. So I'm going to have 10 and 3, 24. Okay, now, what's 10 break down to? 2 and 5. Okay. Now, there's a list of values that maybe we should have a little bit of an understanding for. So I'm going to just say, I'm going to write value here. Actually, let's do it this way. We've used Excel before, correct? Give you a way to find or have a list of your perfect squares, kind of an easy way. Basically, I'm going to write down in this column here, just go to 20. Okay. And in this column, all I'm going to do is I'm going to say I want this number times itself. So say, and that basically a number times itself gives me the square or the perfect square, right? So the perfect square of 1 is 1. If I do this, that gives me 4. 2 squared is 4. 3 squared is 9. 4 squared is 16, right? Okay. Go all the way through here, and those are our perfect squares. What I've got highlighted there are the perfect squares for the digits between 1 and 20. Okay. Those are the ones that you're going to see kind of most frequently as we progress through an Algebra 2 course or an Algebra 1 course or whatever. Is there a number up there that's pretty nice in regards to the factorization that we're doing? We were doing 3240, right? Okay, so we had the square root of 3240. You told me 3240 broke down to 10 and 324, right? 10 went to 2 and 5. 2 is prime. 5 is prime. What is 324? It's not prime. It's composite. But it's a perfect square, isn't it? Okay, so perfect square. So what that means to me, a way we can write this now, we could say that radical 3240 is exactly the same thing as radical 2 times radical 5 times radical 324. Okay, but if I square root any of these numbers over here in the right-hand column, these perfect squares, they are going to give me the integer in the first column, right? So what's the square root of 324? 18. So this changes to 18. So I'm going to put that out in front. Okay. Now I still have radical 2 times radical 5. And those aren't perfect squares, right? So because those are not perfect squares, they go back underneath the radical together. And I get 18 radical 10. Okay. So I know a lot of discussion in doing this problem and talking through it, but the idea is if you can recognize perfect squares, and like I said, 0 to 20 or 1 to 20 are probably going to be your most common right now. But if you can recognize those, it's going to speed the process up for you in regards to simplifying. Because right there, we had 3 factors. Okay. If we don't recognize that and we just say, okay, well, 324, let's go 324 divided by 2, right? So 162. And then we go 162 divided by 2. Be 81, right? 81 divides by, most people are going to say 9, right? 9 and 9. And then 9 goes to 3 and 3. And then 3 and 3. So now we've got 2. There's another 2. There's another 2. There's 4 3s. And there's a 5, right? Okay. So then we group pairs of the same number. So there's a pair of 2s. I can come out in front of my radical. There's a pair of 3s. I can come out in front of my radical. There's another pair of 3s that can come out in front of my radical. And the 2 and the 5, they do not have pairs, so they go underneath the radical, right? What's 2 times 3? 6 times 3 again? 18. 2 times 5? 10. Same answer, right? But this factor tree is a little bit longer, and this process of grouping things is a little bit more involved. Is it okay? Another way of visualizing this is to think, okay, so if I have this 3240, we know that that is 2, we said it was 2 times 2 times 2. Well, how many 2's do I have there? 3, and it's multiplication. So we can consider this repetitive multiplication using exponents, right? So that's 2 to the 3rd. How many 3's do we have? 4. So I'm going to rewrite this as times 3 to the 4th, right? And then we've got just the 1 5. Okay, so we can do that. Now what I would suggest doing is rewriting this. So basically what I want to do right now is I want to say, if I want to take the square root of 3240, right here, that's the same thing as taking the product or the square root of that product, right? Does that make sense? Let's do this. It's 2 to the 3rd. Okay, that means 2 times 2 times 2, right? Well, is that equivalent to saying 2 squared times 2? Is that okay? Is 3 to the 4th, is it the same thing as saying 3 squared times 3 squared? 3 times 3, and then times 3 times 3 again? Then I've got my times 5. So I could do this. All 3 of these versions are the same right now. And now I could do this one more thing down here. 2, I could break this up, each one of these things into their own radical. Okay, and what does if I've got some number down here, I'm just going to put the hashtag sign. If I put that there, the pound sign, and I square it, and I take the square root of that, what is that going to spit back to me? No matter what you put under here. You put a star under there, put any symbol under there, any letter, any number. What does the power of 2 and the square root of 2 do to each other? Cancel each other out. They're inverses. So it leaves me with just the number that's underneath. Okay? Convince yourself of that by taking, on one of your calculators, you can say, I'm going to do a square root of, 3 squared. And it gives me 3. Go 31 squared. Gives me 31. Gives me 31,421, right? Okay, so it doesn't matter what that number is if you're square rooting a square, because basically what this is saying right there, everything that I have highlighted is a perfect square. Okay, it's just not usually written in that way. So if I put, so one of the perfect squares that we know real well is 100. We should know that's 10 times 10, right? So writing it as 10 squared is still writing it as a perfect square. And the square root of a perfect square is simply just that number right there. And in this case, 10. So the reason we would do this is because now, can I cancel that one with that and leave just a 2? Cancel this one with that, leaving me just a 3. Cancel that one with that, gives me just a 3. And then I've got the 2 and the 5. They don't cancel, so they go back together as 10 underneath there. I get 18 radical 10 again. Okay? That logic is going to be very important for us because in the next couple days, I'm going to take away numbers. It's not going to be 2 to the third anymore. It's going to be x to the third. It's not going to be 3 to the fourth anymore. It's going to be y to the fourth. Okay? And we have to be able to understand what we're doing with those things. If we can understand it with numbers, it makes it so much easier with variables. Because variables are still just treated as numbers. We just don't know what they are. Let's do it this way. So if I take, let's see here. Let's change this 10 to the second. Let's raise it to the 4th power. That gives me 100. What's another way I can write 100? With exponents. 100 squared, right? Okay. What if this number was, let's say, 5? So 5 raised to the 4th, but take the square root of that, I get 25. Well, what's another way of writing 25, but using exponents? 5 squared, right? What if this number was 7? Square root of 7 to the 4th ends up being 49, right? What's a way to write 49 using exponents? 7 squared. What are you recognizing every single time we do that about taking, so if this was x to the 4th, you're always getting then what when you take the square root of that? X squared, okay? So the idea is that x to the 4th, the square root of x to the 4th becomes x squared. Is that okay with everybody? Okay, and the reason for that is because x to the 4th is the same thing as x squared times x squared, right? And that turns into the square root of x squared times the square root of x squared. They cancel there, and what's x? It leaves me x times x. What's x times x? X squared. Okay. Let's do another one real quick. Let's say we go to the 6th. I get 343. Any guesses? Because this was a 4 initially, and it came to a 2 when we did 4 and 2. Any guesses of what this should be to get 343? I'll go the other direction. 3. You double it, so take half of it, and you get 3. Okay? So what are we seeing? You know, if this is 8, let's go 78. I get that number right there. So then 78 to the 3rd should give me the same thing, right? 6 and 3 are half of one another, right? Okay. We were seeing 4 and power 2 being half of one another, right? So let's go, let's say we get something real crazy. Let's go 48. Okay, 78 raised to the 48th power. Taking the square root of that then. What is this one going to be? 24. Okay. So the idea here is that every single time that I take a square root of something that has a power on it, if it's an even power, so let's say a square root of 312 raised to the 12th power. That is going to be equivalent to 312 raised to the sixth. Always take half of that number right there. Does that kind of make sense? Okay. And that's what we were seeing here. Okay. When I had 3 to the 4th, I could have written this as 2 cubed, 3 to the 4th, times 5. And then, so this one here, because that's a 4 and that's a square root of 2, they're going to cancel and basically cut that 4 in half and give me 3 squared, right? What's 3 squared the same as? Is it 9? Is that 9 right there? Okay, so square roots, in my opinion, there's a lot of different ways that you can view them and manipulate them and simplify them. And if you pigeonhole yourself into learning one and only one way, if all you do is say, I'm going to learn this structure right here, and that's what I'm going to live by or die by, eventually you're going to die by that a lot, okay? Because when we start bringing in variables, it's a little bit more difficult to do, okay? Or maybe more time consuming to do using this technique. Does that make sense? Okay. We'll stop there for today. I anticipated having an assignment, but we didn't get as far as I wanted to. So I'm going to close that. It's not going to be open for you. Make sure tomorrow you come to class with your computer.
Any particular reason why?
Because I want you to.